Welcome back to Calc 2. This is 8.4 trigonometric substitutions. So in this video we're gonna learn how we can solve integrals that have radicals in them. Now, please understand when I talk about an integral with a radical, you already know how to say do an integral. Let's suppose I put a radical down here of x squared plus, let's do 4. Now, if an integral has, remember, a function with the derivative of that function somewhere, in this case, the derivative of x squared plus 4 would be 2x, already built into the integral, and you see that, this becomes a simple u sub problem, correct? Because we can then let u equal x squared plus 4. Oh, du is 2x dx. So when I sub it out, I'm just going to get 1 over radical u du, which is integral of u to the negative 1/2 du, and that's something you can integrate. So as we get through some of these more complex integrations, please don't forget to look for the simplest first. What I mean by that, don't just assume, you have to go through this entire trig substitution or memorize all your inverse trig or inverse hyperbolic trig functions. Sometimes they're as simple as a u sub. Recognize that. What we're going to look at today is those problems that are not as simple as a u sub. So, for example, if the integral above looked like this, we do not have that function and derivative of function pair that we could use. So remember, for u sub to work, you have to have a function, such as u, and the derivative of that function in the integral. And the derivative has to be in the numerator. That's the other thing to recall with u sub. If the derivative is in the denominator, then you have 1 over du, and that doesn't work when you get down to this part, when you get down to the final integral when u's been subbed in. So what we're going to look at today is integrals that look something like the one I just gave. So we will come back to that one. But first, we need to do a little recall of our Pythagorean theorem and our basic trigonometric functions. So we're all familiar with our right triangle, right? Because these trig substitutions, this is different from trig identities. We're not substituting trig identities in for another trig function. This is completely different. This is we're going to work around our right triangle. Now in the textbook, if you review those notes or take a look at the video in MATLAB for the textbook, it's going to go through a very specific case-by-case method. And it kind of causes you to then memorize all those cases. I'm going to show you a different method where I'm hoping you can just use the knowledge you already have of the right triangle and the Pythagorean theorem and your basic trig ratios. So it will do less memorization. And in this case, you just have to remember a single process. So if you prefer the memorization method, by all means, take a look at what's done in the textbook and take a look at the video in MATLAB for 8.4. All right, again, very, very quick review. We have our hypotenuse and we have legs, right? And usually we identify an angle. So we're going to identify alpha as our angle in the lower right-hand corner. When we do that, we usually also identify letters like A, B, and C. We always make kind of C the hypotenuse. All right. And as everyone is aware, of course, A squared plus B squared equals C squared. All right. And of course, you were also aware sine of alpha is always opposite over adjacent. Right? Cosine opposite over adjacent. Sorry about that. Hopefully you're all sitting there watching the video like, what is she saying? Hypotenuse. Cosine is adjacent angle over hypotenuse. And tan is opposite over adjacent. And of course you also have your reciprocals of those functions. So don't forget, cosecant is your reciprocal of sine, secant is your reciprocal of cosine, and cotan is your reciprocal of tangent. The other thing I want you to recognize is what happens when one of these ABCs are an unknown. So let's suppose we needed to find A. Well, A, right, will be equal to, take a look at your Pythagorean theorem, the square root of C squared minus B squared. B, of course, would then be the square root of C squared minus A squared. And then, of course, C is very different. When you're looking for that hypotenuse, you're just taking the square root of A squared plus B squared. So a couple things I kind of want you to notice about what we just did. Please notice that when we are looking for one of the legs, anytime there's a difference, here, let me do this. That means the hypotenuse is always written first. And when you have a plus, that means you are given two legs. So a couple things to notice. Hypotenuse is always written first in the difference problems. And when you have a plus, that means the A and the B represent the legs, right? So in this one, A and B are legs. Remember, this is an A squared, so you would have to take the square root of A squared to get your leg, so on. And in that one, this C is the hypotenuse. The very first you see is the hypotenuse and then minus the other leg. Okay, the best way to kind of go through this procedure is me to just take you through a problem now. So hopefully you have this written out in front of you. This is just, again, quick recall. So how does this help us solve an integral? So we'll very slowly go through that one I put up earlier, which was just a basic integral. Let's put 36 up here. And let's do the square root of x squared plus 4 dx. So you're looking at this problem, you've already identified, can't use u sub. I don't have a 2x. I need a 2x or some version of a 2x in the problem. I don't have that. And, you know, maybe you can do one of your inverse trig functions, but that was a lot to memorize, so we're not going to go that route. Here's what you do. When you come up with something like this, you think, I wonder if I can use trig substitutions. Draw yourself a right triangle. All right, put your angle in that lower corner. We'll use alpha. You can use alpha, theta, whatever you want for your angle. Ask yourself, X squared plus 4. What parts of the triangle does that give me? So you come up to this, oh, plus. That means A is my X. Do you see that? B must be 2. And this radical, that's the hypotenuse. All right? Because it's a plus, right? Because it falls into this right here, then that is your C. So in other words, that entire X squared plus 4 radical is your C. So go ahead and put it there. I'm going to put 2 here, and I'm going to put X here, and that really doesn't matter which way you go with that. It'll slightly change your trig functions, but not going to be that much of a difference. Once you fill it in appropriately, the most important piece is the constant. And again, it doesn't matter if you put the constant at the bottom, if you put the constant on the side. I just happen to put it at the bottom. So what do I mean by that? Now, I want you to draw a pairing around the constant. So my first pairing is between the constant 2 and the hypotenuse. And then my second pairing, I'll do in blue, is going to be around 2 and X. So the important piece is to make sure the constant is in both pairing. When you do that, now let's do the red one first. We're going to write a trig ratio that matches that pair. So the ones in red, if you come up here, right, I have adjacent and hypotenuse, right? So from my alpha, I have an adjacent and a hypotenuse, so that's a cosine. Cosine of alpha equals 2 over radical x squared plus 4. And then, from alpha, I have an opposite and adjacent, so that's going to give me tan alpha equals x over 2. This is where the substitutions are going to come from. So far, nothing here is new except the process, because you already know how to set up a right triangle. You know your trig identities. As long as you develop write out two trig ratios that both utilize the constant. All right, that's the goal. All right, so what do we do with those trig ratios? Well, watch. Let's start with our tan one. Let's use tan alpha equals x over 2. Well, all I need to do is solve for x, right? Because again, we're doing substitution. So it's kind of like along the lines of a u sub, but we're going to do a lot more substitutions than you do with a u sub. So that means I need to find an x. X is equal to 2 tan alpha. And when we do substitutions, it's not just x we need to sub out, we actually also need to sub out our dx. So let's come up with a dx, because the most basic trig ratio, and when I say basic, when you look at the one in red, cosine alpha equals 2 over radical x squared plus 4, and tan alpha equals x over 2, the one in blue is way more basic, way easier to get a function and to develop a dx. So now what I want you to do is find the derivative of x with respect to your angle. So in other words, what are we finding? dx d alpha. If you used theta as your angle, you're going to find dx d theta. It doesn't make a difference. So, well, what's the derivative of a tan function? That's just a secant squared alpha. Normally, we want to get dx by itself. So I'm going to take this d alpha part and put it over here. What we've done now is been able to get a substitution for dx. Now let's use the other function, cosine alpha of 2 over radical x squared plus 4. And this one's kind of nice because I don't want to sub out x. I don't want to do x. I want to actually turn my entire square root of x squared plus 4 into a trig function. I can do that. I can substitute it out by simply solving for the radical x squared plus 4. So if I come over here and isolate, multiply both sides by radical x squared plus 4, then divide both sides by cosine, don't I get radical x squared plus 4 equals 2 over cosine alpha? I'll take a look at what we have. We have a cosine alpha on the one side, but on my dx I have a secant, but I can turn cosine into secant. Right? What I've done is come up with a way using information I already knew, Pythagorean theorem and basic trig ratios at this point, to rewrite this integral as 36. Oh, what is radical x squared plus 4? Radical x squared plus 4 is 2 secant alpha. Oh, what does dx equal? Dx equals 2 secant squared alpha dx. Okay. Trust me, we have to go through a couple examples, and once you get the practice of it, it's just the process you need to remember. I can simplify this. I've got a squared. I've got 2's I can get rid of. I can get rid of this whole secant and that squared. So what does that leave me with? Integral 36 secant alpha, and sorry, I accidentally wrote dx up there. It's d alpha. D alpha. Now, if you look at your notes from the last video, you will see we actually calculated the integral. Oops, my computer lagged a little bit. We actually calculated the integral of secant alpha, because remember, 36 can just come out front of d alpha. We actually calculated the integral of, well, I think I used secant theta in the last video. It doesn't matter, secant theta, secant alpha. This was a tricky one, but there's a reason I did it there. And we did it by taking secant and saying, this was a kind of a crazy one, because in order for it to work, we had to multiply by secant alpha plus tan alpha over secant alpha plus tan alpha. Because what we're really doing is multiplying by 1. What that gave us was a way to use our U sub process. And the reason we do that is it gives us a secant squared and it gives us a secant alpha, because by multiplying it out, oh, we get secant squared alpha plus secant alpha. And we already did this in the last lesson. This is one of those kind of tricks I showed you that you kind of keep in your toolbox to help you integrate. Because in doing that, if you let u then equal the denominator, you can see real quick that the numerator is right above you, because the derivative of secant is secant tan, and the derivative of tan is secant squared. So you end up with, if you recall, 1 over u du, which is the natural log of u plus c, which equals the natural log of the original u, secant alpha plus tan alpha plus c. So that's just one of those little tricks that comes up. But we'd already done that in the last lesson, so I thought it would be good to use here. All right, so I'm going to go through a couple examples with you, and hopefully you'll start to get the hang of it, and then we'll go back and see how some of these can actually be done using your hyperbolic inverse functions if you choose to memorize those hyperbolic inverse functions. That's a big if. All right, example 2. This one will go ahead, and we don't do definite integrals too often. Let's go ahead and do a definite integral. We'll go from radical 2 to 2. And let's put it in the numerator this time. X squared minus 1 over x dx. So again, when you know, at the end of this chapter, at chapter 8, the whole idea is to be able to look at any integral and try to come up with that plan on how to integrate. So one of the things you might look at when you're looking at this, well, wait a minute, I have a function and a derivative because I have x squared minus 1 and the derivative of x squared minus 1 is just 2x. Well, I have the x part. The problem is if you attempt to use u sub here, I'll show you, you know, you'd have the 1/2 out front because you got to introduce a 2. Actually, you would have to, it would be 2 because, oh, sorry. This is just supposed to be a plain 2 up here. We'll get to that. Let me finish this. All right. Your u would be here, right? Your du would be down here, because, you know, you'd have to put your 2 here, so which is actually 1/2, so I'd have to put a 2 out front. You can't integrate that because we don't have a way to integrate of u times 1 over du. You cannot have the du in the denominator. So that's why your u sub does not work. Even though you've got that pair, it's not going to work for you. So we got to forget u sub for this particular problem. Oh, if you go back to the beginning of your notes, you have a pairing. Let's get that right triangle made. I'm going to switch to a theta this time. Doesn't matter again. X squared minus 1. Remember, when it's a minus, it has to be one of the legs. So the radical x squared minus 1 needs to be a leg. Doesn't matter which leg you make it, just make it a leg. Remember what we also said at the beginning in the notes is the first term is the hypotenuse. It's always your c squared minus a or b, and then the square root of 1 is just 1. So it goes this way. Draw your pairings. The pairings must come because the trig ratios must come from the constant. So there's one pairing, right? And here's another pairing. So what are the two trig functions I'm going to write related to those pairings? If I go for my theta, I would have tan, right? for the red one, tan theta equals 1 over x squared minus 1. That's the one that's going to substitute out our radical x squared minus 1. We can finish that off, right? Solve for x squared minus 1. You start to see a pattern here. X squared minus 1 equals 1 over tan theta, which is, we don't like to write, cotan theta, right? There we go. Now we have something to replace the radical with. But on the other side, here we have our blue pairing when you go from theta is going to be opposite over hypotenuse, so that's a sine, right? Sine theta equals opposite over hypotenuse, which gives us x equals simply 1 over sine theta. So for us to do the derivative, it's easier to turn it into a cosecant theta. And remember, this is the one we're going to use to get our dx substitution. So dx is going to be the derivative of cosecant theta, which is negative cosecant theta cotan theta. And don't forget d theta at the end, because it's dx, derivative of x over d, derivative of theta, dx d theta. So the d theta moves to the other side. Okay? So once you have that done, you can come over and just do your substitution. So what does this integral end up looking like? So going from radical 2 to 2. And now I'm going to plug in cotan theta. Right? That's going to be my radical x squared minus 1. And that is over x. We didn't substitute. Well, we can substitute, actually, for x. What does x equal? We didn't have an x in the last one, but we can turn everything into trig functions because what is x? X is right here. X is cosecant theta. So let's go ahead and do that. Cosecant theta times, I'm going to move the negative out front so we don't need to worry about it. Cosecant theta cotan theta d theta. All right, so we've gotten rid of everything that has an x and we turned it into our trig functions by using what x equals here, what dx equals, and what the radical equals, which we will always get from our trig ratios. Simplify it. Usually a whole bunch of stuff cancels out. In this case, just the cosecants cancel. And I have cotan squared theta d theta. And this is nice. We don't often work with cosecant and cotan. We tend to work with secants and tangents. So this is a good change. Do notice, of course, you know, when we're doing integrals and derivatives, sine and cosine are pairs, secant and tan are pairs, cosecant and cotan, of course, are pairs as well. It just happens to be a pair we don't see as often. But, sorry. We can't just take the integral of cotan squared. We don't have anything for that. But what we can do is turn our cotan squared into, by using our Pythagorean identity, cosecant squared minus 1. Why is that helpful? Because I can take the integral of cosecant squared. The integral of cosecant squared is cotan squared. Okay. We can reduce negatives here by simply multiplying this negative. It's just a way, sometimes you get caught up with way too many negatives. I can multiply that through and distribute it through. If I distribute it through, it just makes this 1 minus cosecant squared. I don't know. I like reducing negatives. Okay. What's the integral of 1? Well, it's d theta is going to be theta. The integral of cosecant squared is negative cotan squared, so that actually becomes plus cotan squared. Or cotan, not cotan squared, sorry. Right? Because d dx, recall, d dx, or integral. Well, yeah, we can look at it that way too, but the integral of cosecant squared d theta is negative cotan theta. Okay? And we're going to go from radical 2 to 2. Now, here's where you need to pay attention to what you did with u sub. For us to keep it from radical 2 to 2, I have to change my thetas back to x's. Or I can change my radical 2 to 2 by swapping the boundary to now a theta. All right, so we did this in u sub. So let's go back. I prefer to change my boundaries because if not, I have to then substitute sine inverse for theta because I got to change a theta into an x. I'm going to change cotan theta into x, which you would do by using this equation right here. But let's go back and change our boundaries because I think that's much easier than having to remember to do everything. So remember, we switched everything from x's to thetas. So what we need to do is switch our boundaries, which are x's, to thetas. So when x equals 2, all you have to do is use this piece. It's the easiest one to use. Okay, sine of theta equals 1/2. So you can use your calculator. I would keep it in radians, or you can do your quick, remember which 1, 2, radical 3. That would end up being the angle pi over 6. So theta equals pi over 6. So this upper bound of 2 actually becomes pi over 6. And when x equals radical 2, I have sine of theta equals 1 over radical 2. Oh, that's your 45 degree triangle, so that's going to end up being pi over 4. So if you're not used to your trig ratios and these 45, 45, 90 triangles and these 30, 60, 90 triangles, you should review those. Basically, it's a unit circle. All right. So that's an important step. By doing that, I do not have to change my thetas back to x's. I can now just evaluate this from pi over 4 to pi over 6. I think that is easier than going in the other direction. All right. Or, remember the other option is to change it back to x's. So what does theta equal? Theta actually is, if you look at this green here, sine inverse. Theta would be sine inverse x. And what does cotan equal? That's right here. Cotan equals square root of x minus 1. Or square root of x squared minus 1. And you would have to take that. Then you could take that from radical 2 to 2. These are both, these two right here are going to evaluate to the exact same thing. So it's up to you what you want to do. All right, but you got to pick one. If you change your boundaries, then you need to keep it as theta. if you put everything back in x's, then you would not change your boundary. All right. So we do that with U sub. We need to do that with trig substitutions. You do that with any substitution where you're changing the variable you're integrating. Again, either way doesn't work. I'll do the top one, and then you can go from there. Again, they're going to both come out exactly the same. So let me get rid of that box. If I integrate the top, I get what? Pi over 6 cotan of pi over 6 minus, and then I would distribute the minus through. I always draw these little triangles, so, all right, cotan of pi over 6. Well, here, if you notice, I already drew my pi over 6 triangle, so I can just say, oh, cotan of pi over 6 is just is adjacent over opposite, so it's square root of 3 over 1. So that gives me pi over 6 plus square root of 3 minus pi over 4. Can't do anything with that. That's a 45, 40. So cotan and tan of your 45, 45, it's the right triangle that has the legs that are exactly the same. So when you do the ratio of adjacent over opposite, it's just going to be 1. You're just going to get 1 there. Okay. So we can bring that together over 1 fraction is fine. However, you want to work that out. If I brought it together and put everything over 12, right? So that becomes 2 pi. It becomes 12 radical 3. That actually becomes 3 pi minus 12. Okay, either way. All right, and if you work out this, you'll get the same answer. All right, so I'm going to go through, for the rest of the video, a couple more examples. What you might want to do is, so here's example 3 here. Let's do nx squared over radical 16 minus x squared dx. So what you should really do at this point is pause the video, try to work it out as best you can on your own, and then come back and you'll see it worked out. Okay? All right, so I'm going to do my trig ratio. My trig ratio is over here. We'll use theta again. I start with my 16 minus x squared. That's going to be a leg. So that's the first thing you do. Is it a leg or is it a hypotenuse? That's the first question. That is clearly a leg, so I'm just going to stick it down here. Whoops. I automatically went to rearrange it, and you cannot do that. I don't know why I did that. Remember, when it's a subtraction, it's definitely a leg. When it's a plus, it's the hypotenuse, the radical. The first part of the radical is always the hypotenuse. That's your C value right there. That is always your C. But it's not that value, it's the square root. So we have a 4 and we have an x. And then real quick, you can see, I'm going to put the 4 and the x together. And I'm going to put the 4 to come up with my 2 trig ratios that I'm going to use to do all the substitution with. So from theta, I'm going to use the x and 4. The blue one, I'll do the blue one first this time. So x and 4 is going to give me a sine function, right? Sine theta equals x over 4. All right, let's finish that one off. X, of course, will then equal 4 times sine theta. We know we need to find the derivative of that one. Dx is for cosine theta, d theta. All right. And let's do the other one. So for the other trig ratio, it looks like I have a cosine ratio, right? Cosine theta equals radical 16 minus x squared over 4, which is then, I remember in this one you solve for the radical because that's what we want to substitute out, equals 4 cosine. And let's make sure we have everything we need to sub out. All right, we have a dx, that's right there, no problem. We have our radical, that's right there. But now we need an x squared. So let's come over here and figure out where am I going to get an x squared? Well, that's simply going to be from our x. So we're good. We can do everything. X squared, if x is 4 sine theta, x squared is simply going to be 16 sine theta squared. The radical 16 minus x squared is 4 cosine theta. And my dx is 4 cosine theta d theta. So you can always feel like you did a pretty good job of getting this right if a bunch of stuff cancels, right? And that's what's going to happen here. A bunch of stuff's going to cancel. So let's go ahead and cancel away. I'm going to move my 16 out front. And it looks like I have 16 sine squared theta d theta. All right, so we're going to need a useful trig identity on this one. A useful trig identity. So when I use an identity in the video, that might be one of the ones you want to make sure you write down and you do memorize. Sine squared of x cosine 2x over 2. All right. What it does, this is the power reducing ones we did in the last section. So it removes us having a trig function that is squared because we know we can't integrate sine squared, and puts us into a cosine function that we can integrate. So I'm going to go ahead and plug that in. So these are, if you recall also, there was another power reducing one. It was the cosine squared. You really do need to know these. They were used in the last section. So these power reducing ones come in handy. So you should memorize those. Okay. All right, let's come back. So, well, I'm plugging in 1 minus cosine, so we'll go ahead and plug the whole thing in. So 1 minus cosine 2x over 2 theta, sorry. I'm using theta. So that becomes 8 integral 1 minus cosine 2 theta d theta. So I can split this into 2 integrals to make it easier for you. Doesn't matter. When you do split the integral, the 8 has to carry through to both integrals. And it lets you do a really quick u sub. Let u equal 2 theta, du equals 2 d theta. So you need a 2, which means you need a 1/2 out here. Just lets you kind of see that. So this one is 8 theta minus 4. That actually becomes, if you do the quick u sub, it becomes the integral 4 integral of cosine u du. So it's just sine. And then you plug the 2 theta back in. That's it. Well, at least that's it for the integration. But here's what you need to remember. And even though this is an indefinite integral, Right now, everything's in theta, right? And you come back and you look at the original problem. It's all in x's. So you have to use these substitutions you set up to just rewrite the final. Now the issue, of course, is we have a cosine of theta, or a sine of theta. We don't have a sine of 2 theta. But that's another one of those trig identities that we used a good amount in Calc 2 as well. And it was the sine 2x equals 2 sine x cosine x. So that one is one you also really need to remember. So I can go ahead and make that 8 theta minus 4 times 2. So that actually goes back to 8 sine theta cosine theta plus c. All right, let's look. What does theta equal? Well, if sine theta equals x over 4, theta is sine inverse of x over 4. That's what an inverse function is. Minus 8 times, we just said it was x over 4. Right? Sine theta was x over 4. Cosine theta, if you come back up here, is your radical 16 minus x squared over 4. You can clean that up a little bit. It's 8 sine theta x over 4 minus 4 times 4 is 16 times 8 is 2, so it's x radical 16 minus x squared over 2 plus c. So again, just like with u subs, even if it's an indefinite integral, we always go back and replace our u's with x's. With these trig subs, you have to replace your theta, your alphas, whatever angle you're working with, back with the x's, which I don't think I did in problem 1. So we can revisit that one really quick. I think in problem 1 I just stopped. I jumped a little too far ahead in my notes. So if you want to go back in your notes to problem 1, we left it at 36 ln secant theta plus tan theta. I got so excited to move on to the next problem. We forgot to plug it back and go back. So if you look back in those notes, it's actually 36 ln, and you just had to use secant and tan. So we have them right here. Tan theta and secant theta. So first one I had was secant. So secant theta you can get from right here. Secant theta is going to be your square root of x squared plus 4 divided by 2. So you're just plugging back in. And your tan theta is right there, is x over 2. So it's just that one last step I neglected in the first problem, so just go back and fix that. But yes, you do need to plug those numbers back in. Plug those x values, those x functions, back into your problem for your final answer. This is now our final answer on number 1. We did it on number 2 as you scroll through because we did the definite. We just did it on the last one. All right, I'm going to jump to a little bit different one right now, real quick. I think this is example 4. And this is the integral of dx over square root of x squared plus 4. And the reason I'm jumping ahead to this one is we can do our u sub. So it's a nice base. So why don't you hit your pause and try your trig substitution problem. It's not an overly complicated one. So go ahead and try that. Yeah, in fact, you go ahead and do it and then hit pause though, please. And then when you unpause it, it'll be completed for you and you can check your answer. Okay, so I left you to do that one on your own because hopefully it is almost identical to the first problem we did. couple little variations, but very, very similar. I also wanted to show you something else, and this is where those logarithmic properties come in handy. And the reason I want to show you this is if you're doing a problem and you're looking up an answer in the book, you might have a very different answer than what you have on your paper. So many of you probably, if you did it correctly, you got to this answer or some version of that answer. So what I went ahead and did was I took out the half. Do you see that? I just took out the half from each of those. So I was left with just the radical plus x. And then I went ahead and applied, you know, ln of AB equals ln A plus ln B. My A being a half and my B being that whole radical of the binomial square root of x squared plus 4 plus x. Now, here's another thing that happens when you're dealing with integrals. This constant just means some number. Well, if you have ln a half does not have a variable in it, you can absorb any constant back into C. So basically that actually can be written as ln x squared plus x plus x plus C. So you may see that as an answer in your textbook, which is why I wanted to show it to you. Now, here's something else. Again, we go back to this idea of memorizing. So let me put the original integral back up, which was just dx over. This is an inverse inch, inverse hyperbolic sine. You know, if you did take the time to memorize your inverse hyperbolic formulas, you would see that is one of them, where that, you know, it actually is of the form, the radical is of the form x squared plus a squared, right, where a equals 2. So that's where that 2 comes from. Just comes from the formula. You think, well, how do those two equal each other? They do equal each other because also in 7.3, there's a theorem that states you can write your inverse hyperbolic functions and express them as logarithmic functions. And the sinh function can be expressed as a logarithm. It's ln of x plus the radical x squared plus 1, which comes out very similar to that. So again, you can memorize. It's not going to work for all of the ones. There are going to be ones that don't fit those hyperbolic inverse functions, and you will need to utilize the trig substitution. So again, I know it's been an hour-long video so far, but some of them were just quick examples, and we're going to do one more example. I'm going to leave you to try. It'll be a little bit different, but I will leave you to try it on your own. So I suggest you trying to do different variations. So there's a couple other variations I just want to show you at least. So give it a try, and then so hit pause, give it a try, and then come back. So we have example 5. Let's do dx with an x squared next to the radical. So go for it. Hit pause. All right. All right, so we'll work out this one together. If you hit paused and tried it, great. You can forward along and see if you got the right answer. So I'm going to put alpha there. Clearly, x squared plus 9, that's going to end up in the hypotenuse, right? Which is going to give me a 3 and an x here. My trig functions, I'm going to go through these a little quicker this time. Tan theta is x over 3. X is 3 tan theta. and dx is 3 secant squared theta, d theta. All right. My other trig function using the 3 is going to be cosine is 3 over, remember you only want to use the constant on each of them, x squared plus 9. So x squared plus 9, radical x squared plus 9 equals 3 over cosine, which is 3 secant theta. So looks like we're going to do secant and tan pairs on this one. Come over here. Let's plug it all in. My dx is 3 secant squared theta d theta over x squared. So x squared we have to take from here. So that's going to give me 9 tan squared. And then the radical x squared plus 9 is 3 secant alpha. Sorry, theta. Cancel everything away. The 3's cancel, so I bring out the 1/9 secant. So what do I have? A secant over a tan. What these essentially become are then problems in the last chapter where you got to figure out what to do. I do not have a u to u pairing, so u sub isn't going to work here. When you end up with fractions like this, sometimes the easiest way to deal with it is to turn everything into sines and cosines. So you can always try that. If we turn everything into sines and cosines, and you'll see why the sine and cosine thing works nice. That ends up being 1 over cosine theta. Tan squared is sine squared theta over cosine squared theta, right? D theta. Multiply top and bottom by cosine squared. You're going to get cosine over sine squared. Why are sines and cosines so nice? Because they are derivatives of each other. We can use our u sub. Because remember, when using u sub with a rational, with a fraction, you always want u to be the denominator. Right? So du equals sorry. Sorry, u only equals sine. I don't know why I put sine squared. It wouldn't erase for me. There we go. U equals sine theta, du equals cosine theta, d theta. So when I plug that back in my u's and du's, I end up with 1 over u squared du, which is 1/9. Don't forget the 1/9. U to the -2 goes up to u to the -1, divided by -1. So it's -1 over u plus c. And you don't forget to. Now, when you do a u sub inside a trig sub, you're doing a lot of substitutions at the end. Don't forget that. All right, so let's move it over here. Okay, so I have 1/9 times, so I'm going to move the negative to the 1/9. U was sine, so I have 1 over sine, but 1 over sine is cosecant, right? Theta. All right, that was my first u sub to get rid of the u's back to thetas, but now I need to get my thetas back to x's because that's what the original integral was in. But remember, we're just doing cosecant, so you can just come back to here, and cosecant, of course, is going to be hypotenuse over opposite. So that's why we have the square root of x squared plus 9 over x, and that's your final answer. All right, so again, I know we've done a lot, but I'm trying to give you a nice broad diverse set of problems here. So let's do one last example. And if you feel good about everything we've done so far, but maybe you want to see this one first, okay? So for this one, let's take a little bit different approach. So now we have dx over 1 plus 4x squared to the 3 halves. When you raise something to the 3 halves, don't forget it's actually the denominator is your radical. So it's radical 1 plus 4x squared. It's that cubed. So don't let that rational exponent throw you off. It's still radical plus 4x squared. All right, so when you do your triangle, right, it's a plus, so it's in the hypotenuse, and that radical 1 plus 4x squared goes in the hypotenuse. So clearly one of your legs is a 1, and you got to take then the square root of 4x squared, because square root of 1 is just 1, square root of 4x squared is 2x. So that's the trig ratios you're going to set up. You're still going to use the 1. So that's going to give me tan, right, theta, we'll use theta, equals 2x over 1, 2x. What does x equal? 1/2 tan theta. So dx is 1/2 secant squared theta. For the other trig ratio, I need to use the 1 and the 1 over. So I'm using adjacent and hypotenuse. So I can go with cosine equals 1 over the radical, 1 plus 4x squared. And I can move the radical over, and again, 1 over cosine is secant. So my 1 plus 4x squared equals secant theta. All right. But remember, we're not replacing just radical 1 plus 4x squared. We have to replace that cubed. So that's going to be secant cube theta. So you just got to recall that when you're putting it back in. Do your substitutions. Your dx is 1/2 secant squared theta d theta. I forgot the d theta over there. I always forget that. Over secant cube theta. Right? Reduce it. And this one actually kind of works out, which seemed more complicated in the beginning, works out very nicely because you have secant squared on top, secant cubed, so it's, I moved the 1/2 out front. 1 over secant, well, wait, I'll need to write 1 over secant because we know 1 over secant is just cosine. And we know the integral of cosine, sine theta plus c. And your last step is to replace sine theta. All you have to do is look at your triangle. Sine is opposite over hypotenuse. So it's 1/2 2x over radical 4x squared plus 1 plus c. So it's x over radical. And whether you write 4x squared, it doesn't matter how you write it. 4x squared plus 1, 1 plus 4x squared, they're the same exact thing. I just think that looks better. Last one, nice, easy one for you, okay? So practice these. Again, you're memorizing a process, so hopefully a lot of the other stuff you already know.